We normally have representations for strong acids and weak acids. So we mentioned earlier that the strong acids are represented by HA. So HA is a representation of strong acid. Now, if you want to represent a weak acid, we represent it by an HB. This is the same thing. It's an acid, but however, the acid is going to be a weak acid. So we mentioned that acids, they dissociate. And by dissociate means that they change into their individual ions once they are dissolved in water. So if it's a strong acid, they're going to dissociate completely. And if they are weak acid, they're going to dissociate partially. For both, for the dissociation, those acids, they do have a dissociation constant, which is K acid. So we no longer talk about equilibrium reactions now, we talk about dissociation constant for Ka. What is this? This is the equilibrium constant for the dissociation of acids. In our case, is going to be a weak acid. So if you look at this equation over here, we have HB. HB is an acid. It's still an acid, but this one is going to be a weak acid. So since we're talking about dissociation, this means that we are dissolving this acid in water. So the acid is going to turn into its individual ions, right? So we're still going to form our hydronium ion or H plus or H3O plus. All of these are the same. So the acid is going to turn into hydronium ion and the B minus, and this is going to be aqueous. So you're going to end up getting your conjugate acid and your conjugate base. It's going to be the conjugate acid, it's going to be the conjugate base. Guys, it really depends. If your acid is weak, as in our case in there, not all of this weak acid will dissociate into ions. Some of it over here will remain unreacted. And if it is HA, strong acid, it's going to dissociate completely into its weak ions. Regardless, so what we're going to end up having, we know that this is an equilibrium reaction, right? So now we're going to develop an equation for the acid dissociation constant, since this is an acidic equation. We know that K equilibrium, K of the reaction, regular K of the reaction, that is equal to the concentration of the products divided by that of the reactants, right? So the concentration of the products divided by that of the reactants. So we know that the products over here are the H3O plus, the B minus, right? And the concentration of the reactants are what? These are HB and water. But remember what did we say about water last time? We said that water is a constant concentration. So we're going to go ahead and we know that this is a constant equilibrium constant or constant dissociation constant, right? So because it is both of these are constants, we're just going to go ahead and multiply those together because K is K equilibrium over here, okay? So that K equilibrium, we are going to multiply it by the concentration of water. And we're going to term both of these are constants, okay? And we're going to call both of these K of the acid. So what is K of the acid? K of the acid is simply K equilibrium multiplied by water. This has a constant value for every acid. And its value is going to differ between one acid and the other. So Ka is equal to the concentration of H3O plus multiplied by the concentration of B minus divided by the concentration of HB. Okay, so it all has to deal with the dissociation of the acid. So you're starting with a weak acid. That weak acid is going to dissociate into its conjugate acid and its conjugate base. Because it is an acid dissociation equation, then the dissociation has to be for the acid, and this is the dissociation constant in there. H3O plus is simply H plus. Okay, so we can substitute this by H plus, and if we do, then in this case we can come up with an equation for Ka, and Ka is the concentration of the acid multiplied by the concentration of the base divided by the concentration of HA. So it's the concentration of the, let's put it this way, conjugate acid, conjugate base, and the concentration of the acid. We can simply relate Ka to the acidity, and we can say that as Ka increase, as the acidity is going to increase. So we look always at the value of Ka, which is the dissociation constant for every different acid, and we look at its value and we compare it to other acids, and we see the largest Ka, the more acidic is the acid, or the larger the Ka, the more acidic is the acid. We can also relate Ka to pKa, and pKa is minus log concentration of Ka, and we would say that as the pKa decrease, as the acidity is going to increase. So the lower the pKa, the stronger is the acid. The higher the pKa, the stronger is the acid. Normally we go with pKa's of acids because the value for the pKa is between normally 0 to 50, between 0 to 50. So we go by the Ka because it is a whole number rather than the Ka, because the Ka values are very small. They are times 10 to the negative 30, negative 34. So we prefer to go with the Ka rather than we prefer to go with the pKa, I'm sorry, rather than the Ka. And we would say that as the pKa decrease, as the acidity is going to increase. There are different types of acids, and as we mentioned, we're talking about the dissociation of these acids in the solution. So it really depends if the acids are strong or they are weak, and it depends how many hydrogens do they have, because not every acid have only one hydrogen. Some of them have more than one hydrogen to lose. So for example, let's start with the first easy acid, which is the acetic acid. This one is called a monoprotic acid. Protic means from proton. Protic is related to a hydrogen. So when we say monoprotic, this means that the acid has one hydrogen to lose. Okay? So when I am reacting this one and this one is dissociating in their presence of water, then the acid is going to lose a hydrogen, and you are going to end up getting the H plus and the CH3 C. I forgot the C over here. The CH3COO minus. This is going to be the conjugate base and the conjugate acid in there. So monoprotic acids, these are acids that give one hydrogen per molecule when they are dissolved in water. So take this one, dissolve it in water. I did not write the water over here, but you can go ahead and write the water. So the water is going to come take the hydrogen and become H3O plus. We simply represent it by an H plus and the conjugate base. Um, Another example of an acid, so this is monoprotic acid, it does have one hydrogen. We can have a diprotic acid. So a diprotic acid is an acid that gives up a max of two hydrogens per molecule whenever it is dissolved in water. So let's have an example, carbonic acid. First of all, for an acid to be diprotic, it needs to have two hydrogens. Okay, so in this case, we're going to go ahead and draw the dissociation of the carbonic acid. So carbonic acid, we are reacting it with water. That's going to be our acid. This is going to be our base. The bronzite and lauric acid, the bronzite and lauric base. So the base is going to come and take one of these hydrogens there, and you're going to end up getting an HCO3 minus plus H3O plus. This is going to be the first dissociation that is going to have a Ka value over here. Okay. But this one over here is going to still has a hydrogen that can still dissociate. So carbonic acid undergoes not just one dissociation equation, but two acid dissociation equation, because this one now it's going to come and act as an acid. This is HCO3 minus that is going to react with water in there, and that is going to dissociate into H3O plus plus CO3 2 minus. Okay, um, so water is going to act as a base, that base is going to come and take this acidic hydrogen. You're going to create the conjugate acid, and you're going to create the conjugate base. So you went from H2CO3. This has two hydrogens that it lost over a period of two dissociation reactions, and every dissociation reaction has its own acid dissociation constant. We're expecting that carbonic acid, this one is considered to be a strong acid as well. Acetic acid is a weak acid. Carbonic acid is a strong acid. Another example, sulfuric acid. Sulfuric acid is stronger than carbonic acid. This one is a diprotic acid as well because it does have two hydrogens that it can lose over two dissociation reactions. So you start with H2SO4, you react that with water. Water is going to be your base. The acid is going to be one of the hydrogens. You start with one of the hydrogens of the sulfuric acid. So the base is going to come and take one of these hydrogens, and you're going to make H3O plus. And you are going to make, that's going to be H3O plus and HSO4 minus in there. This is what's remaining from the acid, and the equation has its own dissociation constant. So now in the second dissociation equation, you take the remaining acid, the remaining acidic hydrogen, which is here, and you react it with water. Water is going to act as a base. And then water is going to come, take this acidic hydrogen, and you are going to make H3O plus, and you are going to make SO4 2 minus. The reaction stops actually. The dissociation stops whenever you look at your conjugate base and you see it doesn't have any more hydrogens to lose. So as long as the conjugate base has hydrogens over here, it's going to keep losing the hydrogens in several dissociation equations. Triprotic acid. This is an acid that does have three hydrogens to lose, and it undergoes three dissociation equations. So the phosphoric acid is going to react with water, and that is going to make hydrogen phosphate. Here you go, plus H3O plus. And then after this is going to be my conjugate base. As long as the conjugate base has hydrogens, it's going to keep being dissociated. So you're going to take this one over here, you're going to react it with water, and you're going to make HPO4. That is going to be 2 minus plus H3O plus. This is going to be the second dissociation equation. So that is going to be Ka1. Guys, these are labeled Ka1, Ka2. So Ka1, this is going to be Ka2 in there. Okay, each one has a number. And then as long as the conjugate base still has a hydrogen, then it's going to undergo a third dissociation. This one's going to be 2 minus. Okay, and you're going to react this with water. Then you're going to end up having a PO4. This is a 3 minus plus H3O plus. Okay, so this is going to be the second dissociation, and that is going to be the third dissociation constant. So H3PO4 undergoes dissociation in presence of water by three separate acid-base equations. Each acid-base equation has its own acidic equilibrium constant. For the common bases, so we said last time that bases are represented by an OH minus. So if you see an OH minus, this is immediately a base. Most of the bases that we're going to talk about, they contain OH minus, and they start with a cation. The cation can be any cation, like potassium, sodium, calcium, magnesium. So cations are always metals in here. They can be polyatoms, by the way. They can be polyatoms. So I can use NH4OH. This one is still a base. This one is a base. Why it's a base? Because it contains an OH minus. The NH4 is a plus a charge. Always bases have ionic bonds between them. When we're talking about bases, nitrogens are bases. So if you have a then this is nitrogen, and the neutral, this is a base. A nitrogen So normally in nitrogen, if it's in neutral, this is going to be a base. Notice here ammonia does not have an OH in it, but it is in neutral. It is in neutral, meaning that the nitrogen has a zero charge. It does have a three bonds and a lone pair. So these are the three bonds and the lone pair. So this nitrogen here is going to be basic. Always nitrogens, they try to be basic because they are less electronegative than oxygen in the chlorine. So it's a weak common base. So if I go ahead and react it with water, we mentioned earlier that that is going to be a base, and we explained why. This is going to be an acid because over here the hydrogen is connected to oxygen, which is more electronegative. So by definition, the base from the nitrogen is going to come and take one of these acidic hydrogens. So you're going to end up getting your ammonium ion and your OH minus. This is going to be the conjugate acid and the conjugate base. When you are doing an acid-base reaction, uh, we are going to use an indicator. So what is an indicator? An indicator is simply a weak acid that you add to the solution of the acid and the base when you are reacting them. An indicator tells you when the reaction ends, meaning when the reaction is going to stop, by simply changing the color of the solution based on the pH of the solution. So an indicator normally is added whenever you have an acid-base reaction, and that indicator tells you when the reaction between the acid and the base stops. And it does that by simply changing color based on the pH of the final solution.